A galactic event of immense significance is rapidly approaching, one that has the potential to astonish the world. Researchers have confirmed that the star system known as Toni Borealis is a ticking time bomb, accumulating material and energy in preparation for a colossal explosion in 2024. This explosive event, known as a nova, will erupt brightly, temporarily outshining every other object in the night sky for several days. This magnificent burst will be visible worldwide, making it a truly global spectacle. Yet, this sudden flare could also signal something far more ominous, a threat that lies beyond our own universe. Let's explore the nature of novas and what makes intermittent novas like Toni Borealis so intriguing. Understanding novas and intermittent novas. While the burst of a nova might seem like a spectacular fireworks display, it hides an unexplained mystery deep within its core. As Toni Borealis prepares to erupt, we must consider whether this seemingly harmless stellar event could actually be a warning sign of something far more dangerous lurking in the vast unknown. In the grand scale of our cosmos, there are many extraordinary phenomena, but one of the most puzzling and fascinating is the nova. These events, though not as catastrophic as supernovae, offer a brilliant celestial show. Novas, particularly intermittent ones like Toni Borealis, have intrigued astronomers for centuries. To truly understand a nova, it's essential to grasp its nature and how it differs from other stellar explosions, such as a supernova. A nova occurs in a binary star system, where two stars orbit a common center of mass. One of these stars is a white dwarf, the dense remnant of a star that has exhausted its nuclear fuel. The white dwarf leads a parasitic existence, siphoning material from its companion star, usually a main sequence star or a giant. This material, typically hydrogen, accumulates on the surface of the white dwarf, where gravity and heat trigger nuclear fusion. The result is an explosive release of energy, causing the white dwarf to brighten dramatically. This sudden increase in luminosity is what we observe as a nova. The key difference: novas versus supernovae. At first glance, you might wonder how a nova explosion compares to a supernova. The main difference lies in the scale and aftermath of the explosion. A supernova is the explosive death of a star, leading to its complete destruction and the release of vast amounts of energy. Supernovae are responsible for creating most of the universe's iron and heavier elements, and can outshine entire galaxies. In contrast, a nova is a surface event that doesn't destroy the white dwarf, allowing it to repeat the process if enough material accumulates again. Recurrent novae, like Toni Borealis, are particularly interesting because they periodically erupt due to the ongoing accumulation of material onto the white dwarf. Unlike classical novae, which only erupt once, recurrent novae can erupt repeatedly, with intervals determined by the mass transfer rate in their binary systems. This predictable pattern makes them fascinating subjects for astronomers studying the mechanics of accumulation and binary star evolution. The cycle of Toni Borealis. For Toni Borealis, the cycle is around 80 years, a brief moment in cosmic terms, yet a significant period for astronomers. Each nova eruption offers a unique opportunity to study the cycles governing stellar evolution and binary star dynamics. But why should we, as mere Earth-bound observers, care about these distant fireworks? The answer lies in the profound insights studying novae can provide about the fundamental processes shaping our universe. The material ejected by novae enriches the interstellar medium with heavy elements, which can later be incorporated into new stars and planets. Furthermore, by studying these systems, astronomers can test hypotheses about how matter behaves under extreme conditions that are impossible to replicate in Earth-based laboratories. Could novas like Toni Borealis pose a threat? While the risks from distant stars may seem remote, there's a compelling possibility that studying recurrent novae like Toni Borealis could help us understand potential threats to Earth. The high-energy radiation and cosmic rays associated with these explosions could affect our planet's space weather in ways we're only beginning to understand. But what if these stellar explosions are more than just brilliant displays? What if they're warning signs of more dangerous phenomena lurking beyond our cosmic neighborhood? Recent observations of Toni Borealis have revealed troubling evidence that this recurrent nova is preparing for another catastrophic explosion. These signs, coupled with the ongoing increase in material accumulation around the white dwarf, suggest that we are on the brink of witnessing a stunning astronomical event in mid-2024. Cosmologists are closely monitoring the system for any changes, particularly in the light spectrum emitted by the star. By studying subtle shifts in the intensity and position of emission lines, they can track the evolving conditions inside the white dwarf's accretion disk, the ring of material spiraling into the dwarf. As the density of this material increases, so too does the likelihood of the conditions needed for a nova explosion, sufficient pressure and temperature to ignite the next burst. What can we learn from Toni Borealis? By examining Toni Borealis and other recurrent novae, astronomers can gain valuable insights into the mechanics of star systems and the broader processes driving the evolution of the universe. Understanding these cycles could also help scientists anticipate future cosmic events and potentially predict systems that might pose a risk to Earth's space environment. Though the likelihood of an immediate threat from Toni Borealis itself is low, its periodic eruptions serve as a reminder of the powerful forces at play in our universe. As we prepare for the next burst of light from this extraordinary star system, we are reminded that the cosmos holds many mysteries, some of which might just be warnings from the vast, dark unknown. Lessell Peltier, an American amateur astronomer known for his dedication to observing comets and variable stars, was instrumental in recording the second extraordinary explosion of TCB. His meticulous observations provided invaluable data that helped space experts confirm the repetitive nature of TCB's nova events. Peltier described the event as an inspiring moment, with the stars rapidly brightening over just a few nights. The involvement of amateur astronomers like Peltier and Birmingham in tracking such events highlights the significant role these individuals play in the field of astronomy. Amateurs often serve as the eyes on the sky, offering early warnings of astronomical changes that might otherwise be overlooked by professional astronomers due to the vastness of space and the sheer number of stars under observation. At the heart of TCB's system is a white dwarf, a stellar remnant that marks the final evolutionary stage of stars not massive enough to end their lives in supernova explosions. These dense objects are typically about the size of Earth but contain mass equivalent to that of the Sun, creating an immense gravitational field that can draw material from a companion star. White dwarfs are essentially the exposed cores of former stars that have shed their outer layers and ceased nuclear fusion. In binary systems like TCB, however, their story takes a dramatic turn. Orbiting the white dwarf is a red giant, a star in the later stages of its life after depleting the hydrogen in its core. This causes the star to expand dramatically, decreasing its surface gravity while increasing its size. The outer layers of a red giant are loosely held by gravity and can easily be influenced by external forces, such as the strong gravitational pull from a nearby companion like the white dwarf in TCB. So, how does material from the red giant reach the white dwarf, and what triggers a nova explosion? The process begins when the red giant expands, bringing its outer layers close enough for the white dwarf's gravity to influence them. This results in a transfer of material from the red giant to the white dwarf, which accumulates on its surface, forming a layer of hydrogen and other elements. As this layer thickens, the pressure and temperature at the base of the material increase due to the white dwarf's intense gravity. Eventually, the conditions become right for hydrogen fusion to occur. This process, which powers stars like our Sun, happens suddenly on the white dwarf's surface rather than continuously, leading to a nuclear explosion, a nova. This explosion ejects the accumulated material, causing the white dwarf to briefly brighten dramatically, making it visible to the naked eye from Earth. As we approach the expected 2024 eruption, historical data from previous explosions in 1866 and 1946 become increasingly significant. These records not only provide benchmarks for current researchers to predict and prepare for the next event, but they also inspire a new generation of amateur astronomers to keep their eyes on the skies, ready to observe and perhaps discover something previously hidden. The scientific significance of the 2024 eruption is substantial. One of the main objectives is to deepen our understanding of stellar evolution by studying TCB's behavior during the eruption. By observing this event, researchers can refine models of how stars evolve over time, particularly in binary systems like TCB. This includes studying the processes of mass transfer between the white dwarf and its companion star, as well as the dynamics of the accretion disk, the swirling ring of gas and dust around the white dwarf. These insights not only enhance our understanding of TCB but also contribute to broader knowledge about the life cycle of stars in binary systems. Additionally, the 2024 eruption presents a unique opportunity to observe the continuous accumulation of material onto the white dwarf's surface as material from the red giant is drawn in. The resulting accretion disk, consisting of gas and dust, will provide valuable information about the dynamics of mass transfer in binary systems. Studying this process during the eruption will help refine models of how mass exchange occurs and how it affects the behavior of the involved stars. Beyond the mechanics of binary star systems, the 2024 eruption of TCB holds significant implications for our understanding of stellar evolution and the role of novae in the creation of heavier elements. The event could offer insights into the potential for a type Ia supernova, which occurs when a white dwarf approaches the Chandrasekhar limit. By comparing this event with other recurrent novae, such as RS-OFF, scientists can draw parallels in their gradual accumulation processes and improve models for predicting future explosions. The eruption will be visible worldwide, even to the unaided eye under optimal conditions. Future studies will aim to unravel the complexities of recurrent novae and their broader implications for stellar evolution. By using advanced observational tools, astronomers hope to gain deeper insights into the processes that govern these explosive events and their role in the cosmic landscape. Triggering the nova, these spectroscopic readings are complemented by photometric data that track the star's brilliance over time. A rapid increase in brightness serves as a clear signal that a violent outburst is imminent, ready to unleash a high-energy catastrophe upon the unsuspecting universe. Toni Borealis is no ordinary star. It's a celestial time bomb, ticking down to its inevitable detonation. This recurrent nova has puzzled astronomers with its unpredictable yet terrifying cycle of explosions every 80 years. This unique binary system, consisting of a white dwarf and a red giant, has previously erupted in 1866 and 1946. As we approach the 80-year mark since the last eruption, overwhelming evidence suggests that another explosion is on the horizon. However, this forthcoming explosion could be even more catastrophic than the previous ones. If predictions hold true, Toni Borealis will suddenly transition from a faint 10th magnitude object, requiring telescopes to observe, into a blinding second magnitude star, shining brighter than some of the most famous stars in the sky. For a brief period, this eruption will offer a haunting observational window into the violent death throes of a dying star system. This short but brilliant nova might finally reveal key insights into the catastrophic forces driving the recurring death cycles of binary star systems. The 80-year cycle of TCB is especially intriguing because of the dynamics of its binary system. The red giant continuously loses material from its outer layers, which then accumulates on the surface of its companion, the white dwarf. As this material builds up, the pressure and temperature eventually trigger a thermonuclear explosion, resulting in the nova we observe from Earth. The process is driven by the mass transfer rate between the two stars and the efficiency with which the white dwarf can gather and compress the incoming matter. Moreover, this upcoming stellar explosion might pack an even more significant impact than anticipated. Later discoveries have revealed not one, but possibly two magma chambers lurking beneath the surface, adding an entirely new layer of complexity to the situation. The primary chamber, known since the 1980s, is nothing compared to the massive secondary chamber discovered more recently. Imagine a hidden reservoir of liquid material, just waiting to fuel future outbursts. Finally, satellite observatories like the Hubble Space Telescope and Gaia are crucial in tracking this impending disaster. They provide essential pristine data, free from atmospheric distortions, offering a clearer view of TCB's behavior and its place in the universe. Gaia, in its mission to map the Milky Way in 3 dimensions, is providing precise measurements of celestial positions, distances, and movements, shedding light on TCB's activities in the cosmos. Now, let's confront the gravity of what we're facing. If the predictions hold true and TCB erupts in 2024, we won't just be witnessing a cosmic event. We'll be observing a live laboratory for understanding the destructive mechanics of such explosions. Astronomers are preparing for what could be the most significant live observational event in decades, studying the volatile death throes of a binary star system. Historical observations of TCB, as we anticipate its potential nova explosion, show us the alarming unpredictability of this binary system. The first confirmed eruption occurred on May 12, 1866, when Irish astronomer John Birmingham, an enthusiastic amateur skywatcher, noticed a sudden brightening in the Corona Borealis constellation. Overnight, TCB went from being barely visible, even through telescopes, to one of the brightest objects in the night sky. This 1866 explosion marked the beginning of TCB's recognition as a recurrent nova. It would take another 80 years to solidify this classification. Fast forward to 1946, when amateur astronomers played an even more prominent role in observing the system, further confirming the erratic and unpredictable nature of this binary star system.